So kinetic molecular theory predicts pressure. Pressure is a result of the collisions between the particles and between the particles and the surfaces around them. Gas pressure makes lots of good things possible. Drinking through straws, inflating basketballs, breathing. Breathing's a really good thing. Moving air in and out of your lungs is possible because of pressure. Variations in pressure of gases in our atmosphere creates wind, and the changes in pressure affect the weather. And that's why the meteorologists are always looking at the barometric pressure, and they're saying here's a high pressure front, here's a low pressure front, because those pressure changes are a big part of what causes the weather to change. So the pressure in general is defined as force per unit area. That's, one of those physics things. So pressure equals force divided by area. And we're not going to do calculations, but it's helpful to understand that concept. So in this jar, we have some gas particles, and they're going to be exerting pressure on the container. In this jar, we have more particles. The area of the jar is the same, but there's more particles. Each particle hitting is going to cause a force. This jar has more force, and so there's going to be higher pressure. Does that make sense? More particles in the same amount of space will give you more pressure. So the pressure is going to depend on a couple of different factors. Number of gas particles in a given volume is one of them. You can get a pressure imbalance in your ears when you fly or when you drive, like if you go up to Grant Grove or Sequoia, you go up in elevation and you feel your ears pop, right? And it feels good when they pop, they cleared up. And if you've got a cold or something and they don't pop, it can be very painful. What's happening? Well, there's air inside your eardrum and air outside your eardrum. And so here's an illustration. As you go up in elevation, the atmospheric pressure decreases. If your eustachian tubes are blocked, the pressure in your ear is still that from the lower the lower elevation, and you get a pressure in your ear which causes your eardrum to bulge out. That's not comfortable. And if you chew gum or yawn or get your eustachian tube to open up, then that excess pressure will come out and that relieves the pain. Then you have the opposite problem when you're coming down, that you have low pressure inside your ear and high pressure outside your ear. And then that causes your eardrum to bulge in, also not very comfortable. And it makes it hard to hear because your eardrum needs to vibrate for you to hear well. And when there's pressure on it and it's bulging in either direction, it's not going to vibrate as well. And that's why I find that going up, my ears pop much better than coming down. Coming down, it'll sometimes take a couple of hours, and I feel like I'm walking around in a tunnel or something because everything sounds funny, right? And then finally, the pressure imbalance is resolved. So pressure is something that can be measured, so of course we need some units for that. The simplest unit is the atmosphere, and abbreviation for this is ATM. That's not an automatic teller machine, but an atmosphere, ATM. This is the average pressure on the Earth at sea level. So at sea level, 1 atmosphere of pressure. Some other units, the SI unit is the Pascal, which is defined as 1 Newton per square meter, so a Newton per square meter. And that's really great for physics, not so useful for chemistry. The Pascal is a much smaller unit. 1 atmosphere is 101,325 pascals. There may be some conversions problems that come up where you'll have to use pascals, but we don't generally use pascals in chemistry. Another unit is the millimeter of mercury, which seems like a very weird unit, Because millimeter is a unit of length, isn't it? How can the length of an element be a pressure unit? Well, we kind of have to do some history on this one. So there was this guy named Torricelli who invented the mercury barometer. And I don't know the details, so I'm just kind of making stuff up here. But I imagine that what he did, well, I know what he did. He took a glass tube full of mercury and inverted it into a dish of mercury. And of course, this was a long time ago, before they knew that mercury wasn't good to play with. It's really fun to play with, though. It's a liquid, and it's a metal, and it's really dense, and it's shiny, and it's just very cool stuff. Unfortunately, it is somewhat toxic. But when you turn a glass tube over, the mercury level will drop, and it will be at a height of 760 millimeters. No matter how tall the tube is, the mercury will be 760 millimeters at sea level. And then, I don't know, how do people get these ideas? He took it up the side of a mountain, and as he goes up the mountain, the height of the column of mercury goes down. And then you bring it back down the mountain, and the height of the column of mercury goes back up, and you get to the same place you were, and it's the same height that it was before. And it's very reproducible. And this was the first barometer. It measured atmospheric pressure. What's happening is that the atmospheric pressure is pressing down on the mercury, and the mercury is pressing down because it's being pulled down by gravity, and the mercury level here will always be at the same. The mercury level is related to the pressure on the outside. If we have lower pressure out here, the mercury will fall down, and if we have higher pressure, the mercury will go up. So I think the easiest way to think of it is that the atmospheric pressure is pushing the mercury up into the tube. Now, if you do this at home with like a drinking glass and water, and kids play with like this in the bathtub. I've seen my kids do it. You take a glass and you turn it upside down in the water, and it's full of water, and you lift it up, and you keep the mouth of the cup under the surface of the water, and the water stays in the cup, right? It's so cool. Look at that. And as soon as you pull it up out of the water, then all the water runs out. If you have a hole in the cup, though, the water won't stay in there. Water is much less dense than mercury. And if you were going to make a barometer out of water, it'd have to be like 34 feet tall. But because mercury is so much more dense, it will only go to a height of 760 millimeters, which is 29 inches. So that's a fairly long distance. So the average atmospheric pressure at sea level will support a column of mercury that is 760 millimeters tall. If the pressure goes up, the height of the column of mercury goes up. If the pressure goes down, the height of the column of mercury goes down. And so this was the first way that they found to measure pressure. And that's why we are kind of stuck with this historical unit, millimeters of mercury. So here's a table of common units of pressure. So it's in table 11.1. It's also inside the back cover of your textbook. I would encourage you to memorize these guys down here, though. It's going to save you a lot of time because we use these a lot. So 1 atmosphere is 760 millimeters of mercury. They also created a unit called a torr in honor of Torricelli, and a torr is the same as 1 millimeter of mercury. So an atmosphere is also equal to 760 torr. So torr and millimeters of mercury can be used interchangeably. We mentioned the Pascal, there's the atmosphere, millimeters of mercury, torr, pounds per square inch. Pound is a unit of force, square inch is a unit of area. That's a pressure. PSI, that's what we're familiar with in terms of inflating bicycle tires and things like that. Inches of mercury is what the meteorologist is going to use. You can convert inches of mercury to millimeters of mercury just like you would convert inches to millimeters. This is in red here because there's an error in the table in your book. So you might want to fix that. Any questions? The way this is set up is that all of these things are equal. So 101,325 pascals is equal to 1 atmosphere, which equals 760 millimeters of mercury, which equals 760 torr, which equals 14.7 psi, which equals 29.2 inches of mercury. So the nice thing about pressure conversions is you never have multi-step problems. You can always do it just in one step. You just pick the 2 units that you need and apply them. And we'll do some examples. Convert 1.25 atmospheres to torr. So we need the relationship between atmospheres and torr. Here's atmospheres, and here's torr. So we're going to use dimensional analysis, 1.25 atmospheres. We can always do these in one step. We'll multiply by torr. We'll divide by atmospheres. We find the numbers by looking in the table. 1 atmosphere, so we put a 1 in front of atmospheres. 760 torr. Notice it says this is exact. They are defined, and so this is not going to affect our sig figs. 760 torr. So 1.25 times 760 equals 950 torr. Now our starting number had 3 sig figs, so our answer should also have sig figs, so I could put a decimal point there, or I could say this is 9.50 times 10 to the 2 torr. It's dimensional analysis, we're just canceling units. Next one, 30.15 inches of mercury equals blank millimeters of mercury. 30.15 inches of mercury times, we want millimeters on top and inches on the bottom. And we go to the table. That's not what I meant to do. This is what I meant to do. So here's millimeters of mercury, and here's inches of mercury. So in front of millimeters is the number 760. In front of inches is 29.92. Our units are canceling out. 30.15 times 760 divided by 29.92 equals. My calculator is saying 765.842246. How many sig figs should I report? 4. This number has 4. 760 is exact, so we can ignore its sig figs, and this one has 4. So I'm going to write this down as 765.8 inches, no, not inches, millimeters of mercury. Any questions? This is the same idea that we used in Chapter 2, converting units, just some new units. Convert a pressure of 173 inches of mercury into pounds per square inch. 173 inches of mercury We're going to multiply by pounds per square inch. The abbreviation for that is PSI, pounds square inch. Divide by inches of mercury. And then we just look at the table and pick the numbers. 29.92 and so 14.9. Does anybody have the table? 14.7, thanks. It kind of looks like a 9. 173 times 14.7 divided by 29.92 equals. Calculator is saying 84.9966578. I'm going to report 3 sig figs. That's going to round up to 85.0 psi. With pascals, especially, they'll sometimes use kilopascals, and the kilo applies to all units in the same way. So if you see one of those in the homework, don't freak out.